Hi everyone, this is a video for class 22 of PH 125, and today we're going to be talking about torque and static equilibrium. So this is the start of a new chapter. This is chapter 11, and this chapter will be all about rotational dynamics and rotational equilibrium. All right, and so the main question that we want to answer in this chapter is what causes rotation? So remember when we first started talking about kinematics, we just talked about motion. We talked about things like displacement, velocity, and acceleration. We called that kinematics. And then we moved on to the study of what we call dynamics, which was telling us about why motion occurs or what causes motion. And what we found is that forces cause linear acceleration. So remember, if we have an object with a particular mass m, then the overall acceleration of that object in a particular direction, so let's say the x direction, is equal to the sum of the forces acting on that object in the x direction divided by the mass of the object, right? So we have this relationship that F net in the x direction is equal to ma net x. Okay, where F net x is really just the sum of the x components of all the forces acting. And we could use that to figure out the net acceleration of the box. And we could do a similar thing if we were interested in motion in the y direction. But then we could understand what happens to the motion of the box by going back to the kinematics. So we learn about what causes the motion, that's the net force acting on the box. And from there, we find that it causes an acceleration. With that acceleration, we can understand things like displacement and velocity, so the motion of the box, using our old kinematics equations. All right, so forces cause linear acceleration and motion, and now we want to know what causes rotational motion. That's our big question. Okay, so it turns out the answer is something which we call torque. Torque is given the symbol tau. It's like a curly T or something like that. It's a Greek letter tau. And it's really defined to be the rotational effect of a force. So this is what allows you to like loosen a nut, or here we have these two kids on the teeter-totter, which is rotating, or if you think about opening a door, you're exerting a torque on the door. So we want to think a little bit more about this idea of torque. So I encourage you, if you have a door nearby, this is a really simple little thing that you can get up and do during this video that will hopefully help you understand torque. It's a little bit of a confusing topic, and so we want to get some visuals in here to help us understand what torque is. Okay, so here's what I want you to do. If you go over to a door and you think about pushing on it, if you push on it harder versus softer, what do you find about how easy it is to make the door rotate? You should find that as you push harder on the door, it's easier to make the door rotate, right? So it rotates more. All right. And so the harder you push or pull, the more the door will rotate on its axis. Now I want you to think about pushing on the outside of the door, or actually try it out. Go over to your door, push on the way outside of the door, so near like the handle, and then try to open the door also by pushing close to the hinge, so really on the opposite side compared to the handle. And what you should find when you do that is that it's much, much easier to open the door if you push on the handle side than if you push really close to the hinge. Okay, and so what this is telling us is that the farther away you push or pull from that axis of rotation, the easier it is to get some rotation. All right, last thing I want you to think about is trying to open the door by pushing in on the door like along the length of the door instead of in the traditional way where you would push like perpendicular to the surface of the door. So if you just push in on the door, you shouldn't get any rotation, right? So there's no rotation that happens when you do that. Whereas if you push perpendicular to the surface of the door, then you get rotation. And so this tells us that if you push perpendicular to what we call the arm of rotation, you'll get the most rotation. If you try to push along that arm of rotation, you're not going to get any rotation. So these effects combined tell us all we need to know really about torque. So first thing, harder you push or pull, the more rotation you get. So that tells me immediately that the torque, which is the rotational effect of a force, it must be proportional to the force itself. So bigger force, bigger torque. All right, next we know that the farther away you push or pull, the easier it is to get rotation. So for this one, we have to define something. We're going to use the variable r. So what r means in this context is the distance from that pivot point or axis of rotation of the thing that's rotating and the place where you've applied your force. For example, if you're pushing on the door, it would be the distance from the hinge to the place where your hand is pushing on the door. That's going to be the lever arm. It has a few different names. I tend to say lever arm. Arm of rotation is also used, and moment arm is the other terminology that can be used for this variable here. Okay, but the basic idea is it's just the distance from the pivot point to the place where you're applying your force. All right, and then the last bit of information here, which is the angle dependence. Remember, so we said that if you push perpendicular to that lever arm or arm of rotation, you get the most rotation. Okay, so specifically what we found then is we need something that will depend on the angle between F and R. So we're applying our force perpendicular to the door. The door is parallel to that lever arm. So the angle between the lever arm and the force is going to be important when we think about torque. That's what we're learning. And specifically, we learned that if we define that angle between the lever arm and the force to be the angle theta, then we would need something that's maximum when theta is 90 degrees, so when the force is perpendicular to the lever arm, and it's minimum in that case where, remember, you were pushing parallel to the lever arm. So really it's going to be 0. You don't get any rotation at all in that case. So we need something that's maximum for 90 degrees and minimum or 0 for 0 degrees. And so that something is the sine function. So this tells us then that the torque is going to be proportional to the sine function. So sine of theta, where theta is the angle between R and F. All right, so let's go ahead and put it all together. So torque, remember the rotational effect of a force. Here I have a wrench, and so it's pivoting around a bolt of sorts. And so that pivot point, the thing it rotates around, we call that the axis of rotation or the pivot point. So here that would be the bolt, that's the thing it's rotating around. And then we are applying a force to the wrench at some length along the wrench, right? So I've applied my force here at some angle relative to the length of the wrench. Okay, so now using our definition that we just came up with on our last slide there, we found that torque was proportional to R, the lever arm, it was proportional to F, and it was also proportional to sine of theta. So in other words, torque is equal to RF sine theta. Okay, so in this case, R is that distance from our pivot point, from our axis of rotation, to the place where the force is applied. So that's going to be our distance R. And then theta is the angle between R and F. So there are actually, you can use two different definitions of theta here. You can extend R, and then theta will be the angle between that extension of R and F. Because the sine function is harmonic, it repeats itself. Actually, you can use this angle in here as theta as well. You will get the same answer when you do sine of theta for either of those two angles. They are not the same. I should call this something else, theta prime. Those two angles are different, but just due to the properties of the sine function, sine of those two angles gives you the same thing. So you can use either one in your calculations. Okay, and so this is our generic torque equation. What we can also do is define something called the perpendicular moment arm. And this is given the symbol R perp, so that's that little perpendicular sign down there below R. And this is the perpendicular distance from the axis of rotation to the force. Perpendicular distance means that it's the distance that's perpendicular to the force itself. So here, if I think about extending the force line backwards, I want to think about the distance from my axis of rotation to that force line such that the distance is perpendicular to the force. Do you see that here? So that's going to be our perpendicular or the perpendicular moment arm. And so if we look at this setup here, I have my angle theta between R and F. And then just due to geometry, we know that that's going to be the angle inside of this triangle that I've formed here with my dashed blue and green lines. Okay, and so then looking at that triangle, that hypotenuse is going to be R, and we have this angle theta opposite to that perpendicular moment arm. And so just looking at this triangle, I see here that sine of theta is equal to the opposite, R perp, divided by the hypotenuse, R, or in other words, R perp is just equal to R sine of theta. Okay, and so what I can do is I can look up here and I see I have an R and I have sine of theta, and so we could replace R sine theta with R perp. So depending on the problem, Sometimes it's easier to think about finding our perp, that perpendicular distance from the axis of rotation to the force. And sometimes it's going to be easier to just use RF sine theta. So it will depend on what you're given, and we're going to practice both methods. So you'll get to play around with it. Really, you can pick and choose whichever method is more natural to you is totally fine. Okay, a bit more information now about torque. So torque has SI units of newtons times meters. So if we look at our definition, R has units of meters, F has units of newtons. So we get a Newton meter in here. Also, really torque does have direction. So traditionally what we will do is go ahead and define the counterclockwise torque. So if a torque causes a counterclockwise rotation, so looking at the force that's applied to my wrench here, it would get pulled upwards. So what you can do is you can think about holding your pencil tip kind of like parallel to the wrench. So your pencil tip is at the pivot point. And then think about pulling your pencil upwards with the same direction of the force that's drawn in the figure here, and your pencil should rotate in the counterclockwise direction. That's how I like to think about the directions of torque. So that would be a counterclockwise causing torque, right? So that causes a counterclockwise rotation. And so here I would say that the torque that's drawn is going to be positive. If instead the torque causes a clockwise rotation, then we say that it's going to be a negative torque. So that's the sign convention for torque. And it's consistent with our rotational stuff that we've been talking about, right? So when we talked about, for example, angular displacement, angular velocity, and angular acceleration, we said those were all positive when the rotation was counterclockwise, right? So this is the same convention here. And last note is that whenever we talk about torque, we always have to define the torque relative to some rotational axis. So some axis of rotation or pivot point. So here we have our bolts, that's going to be our axis of rotation. You always have to define some axis of rotation when you're doing these torque problems. Okay, let's do a little practice. What we want to do is assume that the magnitude of the force applied to each wrench is the same, and we want to think about which one will have the greatest torque on the nut. Okay, so to solve this one, we want to think about the relationship between torque and force, radius, and angle, right? So those are the three things that we know that the torque depends on. So here the force in each case is the same, so that's not going to affect our answers for the three cases. The forces will all be the same. All right, next we know that the torque is bigger for a bigger lever arm. That's like if you pushed on the outside of the door, it was much easier to get rotation than if you pushed on the inside. Okay, so just looking at these immediately then, I would say that case 2 has the biggest lever arm. It also has the biggest contribution from the angle because the force and the radius are exactly perpendicular to each other. And remember, sine of 90 degrees is 1. That's the maximum value of the sine function. So when you have this case where R, which is along the arm of the wrench, is exactly perpendicular to F, that's the case that gives us the greatest torque. So we would get the greatest torque in case 2 here. For those two reasons, F is perpendicular to R and R is the biggest. All right, let's do one more. Now we want to know which one causes the smallest torque. Okay, so we really want to consider the same things here. So we already know that case 2 has the longest lever arm, which contributes more greatly to the torque. So that one's ruled out for the smallest torque. So really the fight is between case 1 and case 3 here. And then remember that we have the relationship that torque is equal to RF sine of theta, where theta is the angle between R and F. And so we want to think about which one has the greatest value of sine of theta here, since case 1 and case 2 have the same R and the same F. Well, sine of theta is biggest when theta is 90 degrees, and that is true in case 1. So I would say that case 1 is going to have a bigger torque than case 3, and so case 3 is going to end up being the smallest torque overall then. So I would pick answer C here. We're going to do more examples with calculating torque in class, but for now we want to think about how torque is related to rotational motion. So remember, our main goal today is just thinking about how is rotation created, right? And so we said that torque is really the rotational effect of a force. And so now we want to know how much rotation does a torque create? That's our next big question. All right, so to answer this question, we're going to go back to Newton's second law, which I feel like we do all the time, right? So we're going to go back to it again. F net is equal to mass times net acceleration. And we know that a net force causes a net acceleration. Now we want to relate this to rotation. So what we're going to do is consider a particle, so like a point mass, that's traveling around on a circle with constant speed. So in other words, we have a point mass in uniform circular motion. All right, so let's start with Newton's second law. F net is equal to ma net. And then what we're just going to do is multiply both sides of this equation by r. We're allowed to do that because we're doing it to both sides, right? So if we can do it to both sides, then we're allowed. So let's go ahead and multiply both sides by r. And then we recognize that we get r times F net on the left-hand side, and that's really equal to tau, the torque. Okay, so we get tau on the left-hand side. On the right-hand side, what we're going to do is remember the fact that the net acceleration for a particle in uniform circular motion, so in circular motion with constant speed, a net is equal to r times alpha, right? So that's that tangential acceleration is equal to r times alpha. And so what we want to do is think about replacing a net here with r times alpha net. Okay, so that's all I've done on the right-hand side is I've replaced a net with r times alpha. And on the left-hand side, I recognize that I have r times f net. Alrighty, and so now what I can do is I can group my r's together. You get r squared on the right-hand side, and really we get mr squared. And I recognize that as the moment of inertia of a point mass in uniform circular motion from our last class. And so this is going to be I, the moment of inertia for that point mass. So what we can do is replace on the right-hand side of this equation r squared times m with I, the moment of inertia, and we're left with the result we were looking for, which is that the net torque acting on an object is equal to the object's moment of inertia times its net rotational acceleration specifically, right? So it's going to be I alpha net. Okay, and when I say net torque, that means the sum of all the torques acting on an object. So torque, remember, is force times the lever arm times sine of the angle between the lever arm and the force. So we're going to end up solving these very similar to how we solved our Newton's second law problems when we were dealing with forces, relating them to accelerations. We always did those same two steps, right? So we always put net force is equal to mass times net acceleration. And then we said that that was also equal to the sum of the forces acting on the object. Here we're going to say that, okay, the net torque acting on an object is equal to the object's moment of inertia times its rotational acceleration, its net rotational acceleration. And that also has to be equal to the sum of all the torques acting on an object, where each one of those torques is due to one of the forces acting on the object. So you'll have to list out the forces acting on the object, and then multiply the force by the lever arm and the sine of the angle between the lever arm and the force. Okay, so that's going to be the basic approach for problem solving in this chapter. So remember when we were talking back in chapter, I think 6, we talked about something being in translational equilibrium. And so this was the case where we said, remember, a lot of problems start by telling us that an object's at rest or it's moving with constant velocity. And those are keywords that should go ding, ding, ding in your brain and tell you that really if we have an object at rest or moving with constant velocity, this is the special condition where the net acceleration of the object is 0, right? Since velocity is constant, acceleration is related to change in velocity, which isn't changing, so we get 0 acceleration. And so since the acceleration is 0, the net force acting on the object has to be 0 as well. And specifically, thinking about x and y components, that the F net in the x direction is 0 and F net acting on the object in the y direction also has to be 0. Okay, so these were the conditions for translational equilibrium, and now when we think about something that can rotate as well, we have to throw in the additional constraint that we can't have any rotational acceleration, right? So if something isn't rotating, or if it's rotating at constant velocity, constant angular velocity omega, then that means that we can't have a changing omega, right? It must be constant. And acceleration, rotational acceleration, is just equal to the change in that rotational velocity. So if it's not changing, or if the rotational velocity is 0, then we have no net rotational acceleration for our object, right? And we just learned that that rotational acceleration is proportional to the net torque acting on an object, and so we must have this condition that the net torque acting on the object must be 0 as well. So we have these three conditions here in the blue box, which combined are the conditions for static equilibrium. So net force in the x direction is 0, net force in the y direction is 0, and the net torque acting on the object is also 0. We'll have to check all three of these in general to solve these types of static equilibrium problems. Okay, and an important thing to note also in solving these static equilibrium problems, which we'll all start by saying, an object's at rest, it's not moving, it's not rotating. Balanced will be another key word. If something's balanced, that means it's not rotating. It's not like, falling to one side or the other. So those will be the keywords to look for on these. So when you start these static equilibrium problems, it turns out that the pivot point, it's not very clear, right? Because if it's not rotating, then what is it rotating around? It's not clear, it's not well defined, but it turns out that you can actually pick the pivot point to be anywhere. Since it's not rotating, it doesn't matter where you pick the pivot point to be. However, there is usually a convenient location to pick your pivot point. So for example, if you have a problem where you're asked to find a particular force acting on an object, but you have two unknown forces acting on your object, you will always want to place your pivot point at the unknown force that you don't need to find, because the torque due to that force will be 0, since the lever arm, the distance between the pivot point and that force, will be 0. So that will cancel out that unknown force for you in your problems. And if you don't need to solve for that force, then that's great. We don't care about that one. So that will generally be the most convenient place to pick your pivot point. Like I said, if you don't pick it at the most convenient point, it's not going to be a big deal. It just might make your problem a little bit harder to solve. And we're going to do some practice with that right now. So here we go. Here's a little strategy for solving these static equilibrium problems. First thing I always want to do when we're solving these static equilibrium problems, we have to think about x components of forces, y components of forces, and we have to think about the forces that contribute to torques. So what I always do is draw a free body diagram. In these free body diagrams, if you're thinking about the weight of an object that's spread out in space, you'll want to draw that weight acting at the center of mass of the object. For example, if you have a beam, that beam has weight spread out everywhere, right? But when we draw our free body diagram, you want to draw the weight acting at the center, the geometric center, or the center of mass of the beam. Okay, and when you're drawing these free body diagrams, remember it's only the forces acting on the thing that's, in static equilibrium that you want to draw. So you don't want to draw any forces that thing is exerting on other stuff. Those don't come into play in our free body diagram. They don't affect the net force and the net torque acting on our object of interest. Okay, so next thing, we know that the sum of the forces is equal to 0. And so we'll have to break up all of our forces that we drew in our free body diagram into their x and y components. And this will give you some relationships between the things we know and the things we don't know. Next up, we want to start thinking about torque. And so to do that, we're going to have to choose a pivot point. So like I said, it can be anywhere in these static equilibrium problems, but there will usually be a place where you have one unknown force acting that you don't need to find, and that's where you want to place your pivot point. Okay, next up, we want to say that the sum of the torques is equal to 0, so you'll have to think back about all of these forces and also where they're acting relative to the pivot point, because that will be key in defining the torques due to each of the forces. Okay, so usually instead of drawing like a real free body diagram, which is you just do a dot and then all the forces act on the dot, I'll start drawing for these torque problems. I usually draw like extended objects. I don't draw just a dot, right? So for example, if we have a plank or something like that, I will draw the plank because then it helps us to visualize where the forces are acting relative to the pivot point. And that's going to be key here in defining the torques. Okay, so then the last step, once we have the fact that the sum of the forces are equal to 0 in both the x and y directions, and the sum of the torques are equal to 0, then we're going to get a bunch of relationships that relate things we know and things we don't know, and hopefully we're going to be able to solve for the thing we don't know that we're looking for. We will, I promise. Okay, so let's do an example. Okay, so here I have a painter. He's 75 kilograms and he's standing in the center of a plank, and the plank is 50 kilograms and 3 meters long, and it's balanced on 2 buckets. Okay, the 2 buckets are both 1 meter from the edge, and we want to know what is the force of support A acting on the plank. Okay, so first step for this, I would go ahead and draw a free body diagram. Here is an example of what I was talking about, where instead of really just drawing a free body diagram as in all of my forces acting on a point, now since we're going to be thinking about torques, it's useful to draw this extended free body diagram. So I've actually sketched out my plank, and I've sketched out the locations where each of my forces act. So here the forces of the buckets both act 1 meter from the edge of the plank on either side. And so since the plank is 3 meters long, that means that there's also going to be 1 meter between the force A and force B. In other words, if we think about how far from the center of the plank each force is acting, they both are going to be acting 0.5 meters from the center of the plank on either side of that center line. Okay, then we want to think about adding in the weight of the person standing on the plank and also the mass of the plank itself. So these would be all the forces acting on the plank. Since the person is standing in the middle of the plank, his weight is going to be pushing down on the plank exactly at that center point. And then remember, this was what I had mentioned, where when we have an extended object, its weight can be considered to be acting right at the center of mass of the object. So here, really, the plank, of course, has weight pulling down on it at each point in space, but really we can just think about the weight of the plank is acting right as it's at its center of mass, which is going to be right at the center of the plank itself. So in the same location that the weight of the painter is acting on the plank. Okay, so we have our free body diagram-ish with plus extra information. And so now we want to think about the sum of the forces acting on our plank. Since the plank is in static equilibrium, it's not rotating, it's not moving at all, it's at rest, we know that the sum of the forces will be 0. Here this is pretty nice because all of our forces are acting in the y direction. We don't have to think about vector components at all. So really what we're just going to get is that F net y is equal to 0, right, since it's at rest. And F net y is equal to the sum of all the forces acting on the plank. So here I have FA acting in the upwards direction. I have FB acting also in the upwards direction. And then I have the weight of the plank downwards. So I'm going to say minus m plank times g. And I also have the painter's weight acting downwards. So this is going to be minus m, let's do painter, times g. Okay, so that means that we have this relationship here between all of these different forces acting on our plank. From there, we still have one too many unknowns, right? So we don't know FB. We're looking for FA, that's the thing we're looking for, but we don't know FB either. And so from here, we don't have enough information to solve the problem. We have to think about torques as well. Okay, so to do that, we're going to choose a pivot point. Here, I'm going to go ahead and choose a pivot point to be the center of the board. And the reason why I'm going to choose the center of the board to be the pivot point is because then 2 of the forces acting on the plank will have 0 torque. Okay, so both the weight of the plank and the weight of the painter will contribute to 0 torque in this case because the distance from the pivot point to the place where those forces are applied will be 0, right? So they're both applied right at that pivot point. And so that means we won't get contributions from the torque from either of those 2 forces, and that's just going to simplify our calculations here. All right. Another useful place, you could have picked the pivot point at FB since that was our unknown that we're not trying to find. So in general, that would be where I normally would pick it. But in this case, because 2 of our forces act at the same location, that's actually going to be the most convenient. Either way will get you there, but I think this is probably the easiest way to solve this one. Okay, so now we're ready to think about the sum of the torques acting on the object. So the object is the plank here, and we know that the sum of the torques is going to equal 0. So let's just go ahead and write out the sum of the torques from each of the forces acting on our plank. So we know that tau net is equal to 0, and it's also equal to the sum of all the torques acting on our plank. So we're going to have 4 torques acting on our plank, and the first thing I just like to do is think about what is the direction of each of the torques. So here let's start with FA. FA is pulling up to the left of the pivot. Remember, the pivot is at the center of the plank. And so I would say that that's going to cause the clockwise rotation of the plank. And so FA is going to cause a negative torque. So let's say negative tau A for the torque due to FA. Next, we have the torque due to the weight of the plank. And so the weight of the plank, remember, is acting right at that pivot point. So that means that there's actually not going to be any torque due to that force acting on this plank. So we can just go ahead right off the bat and say plus 0 for the torque due to the plank, or I would probably call that like tau PL here. All right, next we want to think about the torque due to the painter. This is also acting right at that pivot point. So the lever arm again is going to be 0, and there's no tau painter here, right? So we get another 0. And then the torque due to FB is pulling upwards to the right of the pivot point. And so if I think about rotating my pen by pulling up on my pen on the right side of where I'm holding it, that would be the pivot point, I get a counterclockwise rotation, and so that would be a positive torque. So let's say plus tau B. Okay, and so now we know the signs of our torque. Next step is to figure out the torques themselves. So remember, tau in general is equal to R F sine of theta, where theta is the angle between R and F. So here we could write this out and say it's going to be minus RA FA, where R and F are both magnitudes. So we've already taken into account the sign of the torque with that negative sign. We don't want to put in any more signs here. That will confuse things. We've already taken care of the direction. So R and F will always be positive values. Okay, and so then we have RA FA sine of theta A, where theta A would be the angle between RA and FA. Okay, plus RB FB sine of theta B, where theta B would again be the angle between FB and RB. So let's sketch out RA and RB on our free body diagram, and that will help us come up with those angles theta A and theta B. So let's start with A. The lever arm, remember, is just the distance from the pivot point to the place where the force is applied. So RA is going to be this vector that points from the pivot over to FA. It looks something like this. And the length of RA, the length of that lever arm, is going to be 0.5 meters. That comes from the fact that the pivot is at the center of the board, which is going to be half of the board's length from one edge, right? So that would be like 1.5 meters from the edge. And we're told that FA is acting 1 meter from the edge, so that leaves me with 0.5 meters between FA and the pivot. Okay, so RA is really going to have a value of 0.5 meters. All right, and then the last thing we need to know for the torque due to force A is the angle between RA and FA. RA is horizontal, FA is vertical, so theta A is going to be 90 degrees. Okay, now let's look at FB here. We could draw in RB. It's going to be the vector pointing from the pivot to FB. RB, okay, so it's going to be horizontal, and it's also going to have a magnitude of 0.5 meters. Since, again, FB is 1 meter from the edge, and the center is 1.5 meters from the edge. Okay, so then the last thing is, what is our theta B? It's the angle between RB and FB. RB is horizontal, FB is vertical, so theta B is also going to be 90 degrees. Perfect. Okay, so then we end up with minus 0.5 meters times FA times the sine of 90 degrees, which is just 1, plus RB, which is 0.5 meters, times FB, sine of 90 degrees, which is just 1. So let's go ahead and just put in 1 here. All right, and so those two terms added together must equal 0. Let's go ahead and add 0.5 meters times FA to both sides of our equation. We would get 0.5 meters times FA is equal to 0.5 meters times FB. The 0.5 meters cancel, and we're left with FA is exactly equal to FB. Okay. So that's great. Now we have two relationships that relate our two unknowns. right? So I have this relationship over here from my forces, and I have my relationship from my torques. So I have two unknowns, but it's okay because I have two relationships that relate them. All right, oops, sorry. So now the last step is to just combine this information. In other words, I can just put in the fact that FA is equal to FB over in my equation from F net Y. So when I do that, I want to find FA, so I'm going to go ahead and replace FB here in our equation with the fact that FB is really equal to FA. And so when I do that, what I end up getting is 0 is equal to 2 times FA, right? Since I get FA plus FA, that's 2FA, minus the weight of the plank minus the weight of the painter. So that would be minus M plank G minus M painter times G. So M plank, remember, was 50 kilograms and the painter is 75 kilograms. We can plug those in and solve for FA. And when I did that, I ended up getting the fact that FA was equal to 610 newtons. Okay, so this is our first static equilibrium problem. There are many more to come, don't worry. And we're going to continue practicing thinking about our little painter guy here in class next time. So I will see you then.